Today we are going to look at a simple triode gain stage, and this is a sort of amplification stage that you're going to find in every single amplifier that is out there, in almost all of the instruments that are vacuum tube instruments, and you'll also find it in almost all radio receivers or radio transmitters. Some of them will not have a triode gain stage, they'll have a pentode gain stage, but usually the first stage of amplification in any sort of instrument is a triode gain stage, and it's really one of the simplest vacuum tube circuits that are out there. And there are quite a few websites around that describe how you would go and design one of those, but when I was first learning this, I found it quite difficult to learn, and so I thought I'd make this video to go over some of the basic principles, and maybe it will help someone. So I've got our triode here. I already drew a triode with the anode, grid, and cathode here, which is obviously heated, but so to actually make this into an amplifier, to make this into a simple gain stage, we have to have an input, which will probably come in here via a capacitor. I'll just do this AC coupled, but if you have DC amplification, then just don't have this capacitor. And then we'll have this come out here via another capacitor. And to actually get some sort of voltage here, we need to add a resistor, which is called the anode resistor, or anode load, I think. And that's connected to the high tension. And then we also need to bias the grid somehow, because vacuum tubes are devices that are basically, if the grid is at the same potential as the cathode, then they're fully on. You would almost never drive the grid positive in a sort of hi-fi setup. Sometimes this is actually desired for guitar amplifiers where you overdrive the grid, but in almost all vacuum tube applications, you would have the grid be more negative than the cathode. Because if you make this positive, you will actually get another sort of anode, but at a lower voltage. That will do things to the amplification and to the overall behavior of the vacuum tube. So we need to bias this somehow, and the most common biasing scheme is cathode bias, where we put a resistor here, and what this resistor does is, if current flows through here, then there'll be a voltage drop over this resistor, which will indeed elevate the cathode, and therefore, if the grid is connected to or at ground potential via large resistance, for example, there is no current flowing through here. Well, negligible current. So there is no voltage drop. This will sit at 0 volts. 0 volts in respect to here. But this, in respect to here, will sit at whatever bias voltage is dropped over this resistor. So if you place yourself in the position of the cathode, you see that you are at 0 volts, because this is just a concept. Wherever you put your ground point, there your ground point is. So if this cathode is 0 volt, you're sitting here, then this is actually several volts below what you are at as the cathode. And that's how basically this cathode bias works. So that's all fine, but what we really need to do is find values for this. And I'll do a practical example where This has been done 1,000 times for all sorts of double triodes, like this PCC85 and all of the other small triodes. What's wrong with my camera today? But what actually a lot of people don't know that these ECH84s, I have stock of about 100 of those, and even if I start repairing radios now and don't stop till I drop dead, I will not use up all of these mixer vacuum tubes. But what they have is the ECH, so they have a triode in there, and I think we'll design a circuit today that uses that triode. And we'll not care about the hexode for now. It could be used for other sort of things, but we'll just build a little demo circuit that uses the triode in here. So if we had a double triode like this, we could just go to the internet, get a reference circuit, work from there. But since we don't, we'll get our datasheet here. This is the Philips datasheet. Comes in 3 languages, which is nice, but the important one is the English up here. Typical characteristics of the triode section. It's probably interesting to look in here. 200 volts, minus 11 volts for the grid, 50 volts on the anode, 0 on the grid, 3 milliamps anode current, whatever. And also limiting values. So we shouldn't go over 250 volts. And the cold load can be 550 volts. So good idea is to probably put the high tension around 250 volts somewhere. Maximum dissipation is 1.7 watts. And then there's... Oh, oops, I'm looking at the heptode here. Should have been looking at the triode. So 550, that's the same values, 1.3 volts. Maximum grid resistor, 3 mega ohms. What this also serves is basically with the capacitance of the focus. With the capacitance of the grid, this forms a low-pass filter that keeps RF out of this, which is great because you don't want your triode gain stage to be oscillating with RF. So maximum cathode filament voltage is 100 volts, and maximum cathode current is 10 milliamps. This we should keep in mind as we're designing this, so we don't want to go over these. So here are a couple of circuits, couple of diagrams, which you see. This is the heptode. This is the triode here. You see, this is the voltage on the grid, and this stops at 0 volts. You usually don't want to be driving this positive. You want to stay somewhat here between the vacuum tube fully open and the vacuum tube we call cut off, which is here where there's no current flowing. So really interesting graph that we want to have is this one. And almost all vacuum tube data sheets will have this. And important, this says triode here. Maximum anode dissipation is say 1 watt here, which is probably a good sort of limit. So what these curves tell you is at this grid voltage, for this anode voltage, there'll be, just get a ruler here, this and that much current flowing. So if you look at 250 volts and minus 6 volts, there will be about 1.8 milliamps of current flowing. And what we want to do now is to draw what we call a load line. And a load line is basically goes from having the vacuum tube fully cut off, so the full voltage is on the anode. Which, I don't know, we'll just set it at 200 volts here. And then basically the vacuum tube being a short circuit, so all the current flowing, which, I don't know, would be 4 milliamps and 200 volts. Then we'd drive a line through here. But what we do now is we want to pick a place on these curves where we want the vacuum tube to operate. And for a sort of amplifier that amplifies fairly linearly, we want to be above this region here, where these curves bend. We want the part of curves which are linearly here, up here. And then we also want the one that we, sort of the point that we pick on one of these lines, we want them to be equidistant. So if you have a 1 volt peak-to-peak signal, and you put it somewhere on the -2, you have equal amount of voltage distance, so distance on this axis, if you go positive or negative, if these are equidistant. And that means that, let me just draw on here, if you put in this sort of signal, like a sine wave, then you'd get the inverted sine wave out, which would, I'll just draw it without the inversion because that is probably easier to understand. It would look like this, and then it would be just as much amplified down here, just as much amplified down here. You get the idea. If you put it somewhere where these are not equidistant, so there's much extremer examples on some other tubes, I mean, this is actually still fairly linear. You would get something like this. If you put in this sort of waveform, you get a large amplification here, and then you get a small amplification here. You get large, and like this, which is good for some applications, but it's not good for this. So what we want to do is pick one of these lines here, and then take our anode voltage, which we probably know. Mine is probably going to be around 200 volts in this application that I'm just thinking about. And then we want to draw our line through the 200 volts here and this point on this curve that we pick towards this. I made a mistake here. My application is actually going to have 250 volts of high tension. So we start here, and then we'll just look for a place that looks fairly good on the, I think on the 3 volt curve here is nice. Because if you pick, you could equally put a -1 volt, but if you put it somewhere here, then you'll have a lot of current up here, which you don't necessarily want, because then you'll have your idle current will be very high, and then you have to have a large anode resistor to dissipate all of that. And also, if you're idly at 8 milliamps, you'll stress your tube far more than if you're at 2. So we'll go from the 250 volt point, and I'll just put this sort of here. Could go a little higher, then you'd have a little higher idle dissipation, but this should be fairly good. And then we'll just take these two lines and connect these. Like this. And now we have what is basically a load line. And what this allows us to do is to tell us at 250 volts we want 3.8 milliamps. And then also we want the cathode to be biased at -3 volts. And what you do now is you get yourself a calculator. And what you do with your calculator in place, you write down Ohm's Law. And then you solve for the resistance by dividing by I. So you've got U over I is equal to R. And then you put this 250 volts divided by 3.8 milliamps, and then you'll get 65 kilo ohms for your anode resistor. So this up here is 65 kilo ohms. The nearest standard value to this would be 68, I think. 68 kilo ohm, which is perfectly fine. And now you also need to calculate what your grid bias resistor needs to be, because now you know the idle current and you know that voltage, so you can calculate it. So what you do for that is you basically take your ruler again and you just draw a line from your bias line up here, and you'll arrive at about 1.8 milliamps with your 3 volt bias. And this load line, I think it's actually probably not all that easy to see on camera. Let me just draw this a little thicker. So now we're at 1.8 milliamps, and if we know that, we'll go back to Ohm's law, which is and we'll solve for resistance again. So we'll divide by I. And we have the same equation as above. And now we'll put in 3 volts divided by 1.0 1.8 milliamps, which will give us 1.6 kilo ohms, which will give us our -3 volt bias. And now we've got our basic values here. This is 1.8K, and this, we know from Datasheet, maximum value is about 3 meg. We'll put this pull down at 1 mega ohm. This is just a common value that is used a lot, and it doesn't really matter what you put there. Another thing that we might want to consider is we might want to give this an AC bypass cap, which will basically do the following thing. It will exclude this resistance for all frequencies above the cutoff of this capacitor here, because this will be a low resistance to any AC coming through here, and this will improve the amplification and the gain in a way. I probably might do another video on this. But this is usually a largish value, so the cutoff is fairly low. So for audio, a typical value would be 100 or 200 microfarads. So you have your cutoff well below the audible range. But we'll not talk about this today. But this is basically what we want on building a Triode Gain stage. So we'll go to our tube now, and I put this on a little breadboard. I'll just zoom in here a little bit. So this is the tube, and already pre-mounted these components. Although this is a 1K resistance, I might replace that before we do any measurements, because on my earlier, on me trying this earlier, I drew a little bit of a different load line. So I think it's time we hook this up. An additional thing to note is all of the heptode grids are just tied to the cathode, and that will basically disable them because they sit at cathode potential, so they can't do any harm, but they can't emit any electrons because they're not heated up. So I think it's time we hook this up to some high tension and some heater voltage and a signal, and then we'll look at it on the oscilloscope. As you can see, I put the whole circuit with the ECH84 on a little breadboard, and I already have it connected. So what you see is here I've got the grid resistor of 1 mega ohm. Here I've got the cathode resistor, which I lowered a bit from 1.6K to 1K. And then here I have the anode resistor, which is the next standard value, which is 68K. And the tube is already lit up, which you can't see because the getter on this gets down fairly low, and there's a rather large structure inside because of the heptode. Also important to note is I put all the grids of the heptode that I'm not using, I tied down to ground. So they don't interfere with anything, because if you have them connected to the cathode, I should say cathode here, not ground, to the cathode, then they won't do anything because they're not hot enough to emit electrons, and they don't have a high enough potential to really influence, that is to say, to attract electrons from the actual cathode. So this is the test circuit. I've got a multimeter here, and we'll have a little look at the oscilloscope over there later. So let me just turn this on, and it will take a second for the vacuum tubes in the anode supply to heat up. But we should see that on the meter here very shortly. There we go. And I preset it to 250 volts, which it just overshot. But it's falling. This is the thing with a simple power supply like the one I designed in the previous video here. This takes quite a while to actually stabilize, because there's a neon voltage regulator tube in it that takes a minute to heat up to reach a stable voltage, and all that sort of jazz. So let me just move this over here, because with these hooks you sometimes have the problem if your resistors are dissipating too much current, the leads actually get hot enough to melt them. So that just gives them a little more space. So I'll just regulate this down to about 250 volts. And while we do the measurement, we'll just have a look at this every now and again to see if it changes significantly with the tubes. It's now about half an hour later, and as you can see, it moved only very slightly. So I think we are ready to do some tests on this. And the first thing that I want to do is to basically measure the voltage drop over this cathode resistor here. And it's about 2.58, which is a little low. But this is to be expected. I didn't have a 1.6 or near 1.6 resistor, so I choose a 1K. But this is a little low. So I'll probably just check my resistor box here. I actually ordered some 1.5K resistors, so I think I'll put one of these in now. As you can see, I took the old resistor out, put the new one in, and just have a little look. Now we're at 3.9, which is a little too much, but the power supply has cooled down again, so we'll just check the voltage here. Yeah, this is basically spot on. So 1.5 is almost too much. I think I'd much rather stick with the 1K. Except if I have 1.2K, which I have. So we're just basically zeroing in on that now. Although it's probably not all that important. So I know I've oftentimes in the past I just stuck any old value in, and it worked just as well. As long as you're in a reasonable range. But let's try and do it properly this time. So I'll just desolder this resistor. Put this one in. And then reconnect all our leads. There we go. Now I'll turn the high tension back on, and we'll just see how this goes. And there we are. What's the voltage here? It's 251. That's a little over 3. So I'll call this pretty good. That's what I wanted to have there. So the cathode is elevated about 3 volts, which means the grid resistance, the grid will sit at -3. So I think it's high time we put a signal into the grid here. And I'll do this from a signal generator. That I'll hook up over here. And I'll just connect this to this wire, which has ground potential. This just loops around and connects to all the grids of the heptode that are basically ground potential, so this should be fine. So I'll just boot the signal generator up here, and I'll then turn on the oscilloscope. There we go. And now I will connect the 2 channels. The first channel I'll connect right to the input signal. And the second channel I will connect to the bottom portion of the anode resistor. So basically our output. And is this showing 0 volts now? Well, that is certainly interesting. But there's still voltage on here. Is there a signal coming in from the... Well, I don't know. We'll just roll with that and see what happens. So I'll switch the camera over to basically have a look at the oscilloscope screen. And then we'll feed in a sine wave signal and look what that does. So we are now centered in on the oscilloscope screen, and what I'll do now is I'll just set up my channels while also bumping the camera. So I've got the first channel, the input set to 500 millivolts, and I've got this set to 20 volts per division, and the horizontal frequency I've got at 200 microseconds. The trigger is on auto, and I've got the peak-to-peak voltage for channel 1 and the frequency of channel 1 here. So now I'll feed in a 1 kilohertz, 1 volt peak-to-peak signal, sinus signal from the frequency generator. Let me just turn on the output here, and there we have our signal. It is 1 kilohertz, it's 1 volt peak to peak. And if we go into measure now, we'll just get the source down to, this is actually not ideal, this camera setup, is it? Source channel 2, type, just the peak to peak voltage, frequency should be the same. And then, if I press measure again, no, it's 41 volts. So we have about a 40, a times 40 amplification here, which is quite good. No, it's not triggering properly. If I play with the trigger level here a little bit. That doesn't seem to help at all. No, this is AC coupled. This is also AC coupled. So I'm relatively new to digital oscilloscopes. So if I change this, will that do anything? No, I don't think. Well, no, it's going completely crazy. Oh, I just tapped the tube. So, yeah, is that it? I let everything warm up for a little bit longer and also wiggled the tube a bit, and now it seems to be relatively stable. So what I want to do now is I want to try this at a couple more frequencies. And to start with, I think I'll just go right to the top of the audible range at 20 kilohertz. Obviously we have to adjust our horizontal here. And we still have about 40%, about 40 times amplification. That still looks very nice. What you can also see here is that inherently these are inverse of each other. That's a thing with simple triode gain stages, they do that. And you just have to be aware that your signal will be inverted, which, but in practice, really doesn't matter that much. We'll also, just for a laugh, go down to 20 Hertz. And see, this is still very good, still at 40. Still at times 40 amplification, still represents the sine wave perfectly. Obviously, if you would do like a frequency, a pass frequency of this amplifier, you'd have to get a lot more measurement points, and you have to do a FFT, for example, or use a spectrum analyzer, which I might do in a future video, but this is just a quick test of if this is actually working right. So let's do one more thing here. Let's change this to square wave. And let's see how it does there. Can see that that doesn't really look like a square wave, but then again, the signal generator is not outputting a perfect square wave, and I think the reason for that might be... No, that's obviously not it. I thought I had set it wrong, but okay, this is what it produces. It's also a new frequency generator. I haven't used it that often. So we'll go to 1 kilohertz and hope this is a better square wave then. Yeah, this looks much nicer. But as we can see, especially if we just move this up here a little, this is perfect. This is a very, very nice amplification stage. I'm very happy with that result. Actually, 40 volts of output should be pretty good for driving a lot of power amps. Don't need all that much voltage swing, especially if you're using something like an EL84. That should be plenty. If you're having larger vacuum tubes, then you might have an issue with them actually needing a little screen current, which this setup probably can't provide. If you're driving like a kilowatt amplifier, then this obviously wouldn't be all that great for that, but for most purposes this should be fine. Let's go up to 20 kilohertz. And now we can see that it's a little sloped here where the input signal is not. And that's probably going to get worse if we go up way out of the audible range. Let's go to 200 kilohertz. And now you can see the limitations of this setup, because the input here is perfectly square, but this is not a nice square wave now. So, but we're not going to amplify 200 kilohertz signals with this. We're going to keep it in the audio range, which means we're going to have at most something like this, which if you zoom in, yeah, it's visible and it's definitely there, but it should be fine. Square wave is actually a fairly hard test on an amplifier like this, because it basically has to have a huge and fast rise in voltage here, and then the same here. This drop has to be almost instantaneously. So I call this a good result. And I think in the next video we'll either characterize this triode stage further, or we'll actually have a look at pentode amplifiers. But yeah, I call this a success. So thank you for watching, and I'll see you around.